In this model, the particle is confined from 0 to A on the x-axis with infinite energy barriers on either side. Inside the box, the potential energy acting on the particle is 0. Therefore, the Schrödinger equation only needs to be solved within the region of space defined by the box. Solving this differential equation involves the workhorse mathematical technique of quantum mechanics, separation of variables. We assume the solution is the product of a function of space only and a function of time only. The solution to this well-known differential equation after the separation of variables involves a linear combination of sine and cosine. To find the constants a and b, we must apply the boundary conditions. The first boundary condition requires that the wave function goes to 0 at the edges of the box, at x equals 0 and x equals a. Plugging in 0 for x reveals that b must be 0 because the cosine of 0 is equal to 1 and not equal to 0, which is not a consistent equation. The next boundary condition involves plugging in a for x. So now we have that 0 is equal to some constant a times sine of k of a. For this, we turn to the graph of sine of x. The sine function crosses the x-axis at integer multiples of pi, implying that ka must be an integer multiple of pi as well. Thus, ka is equal to n times pi, and k equals n times pi all divided by a, where n is a positive integer starting at 1. N equals 0 is not a useful solution because it is just another trivial solution. This gets us to the final wave function, which must be normalized. Normalizing the wave function forces the integral of the probability density over the span of the box to be 1. This allows us to solve for the constant a, also known as the normalization constant. The wave functions plotted as a function of position have an increasing amount of nodes as you increase n. In fact, the number of nodes is just n minus 1. The probability density, which is the modulus squared of the wave function, reveals more insight into the location of the particle. Peaks in the probability density plot represent areas where the particle is likely to be found, and troughs are areas where the particle is not likely to be found.